to the cloud. So hopefully that means it's recording. I think it is. I'm using a different device this time, so I never really truly know. Oh yeah, there. Finally, the icon came up. All right, so we're going to learn about measures of variation. So that boils down to two important concepts. Well, sample variance and sample standard deviation, as you can see here. All right. So what I want to do is take you through an example by hand first, and then I'll show you how to do it using technology. Just because it's kind of important to have an idea of what the relationships are that are embedded within a particular process, and we'll use calculators as a shortcut, but it's in our best interest to have a good handle on how to do it by hand, right? At least in the early going. So we're going to focus on the sample variance. The question here says, find the sample standard deviation. But in order to find the sample standard deviation, you have to find the sample variance first. All right, now this is a pretty intimidating looking formula, but I can tell you that if you kind of look at it inside out, it's really not that bad, because this piece here is really just telling us to take each X value and subtract from it the mean. All right. So the first thing I would need to do is figure out the mean of this data set. Right. So the mean you figure out, and you could scratch it out on the side, or you could use technology. This might actually be a good point for me to bring up the Desmos calculator and just show you what I mean by technology. Let's go to Desmos. Oh, wrong Desmos. All right. Desmos.com, just ordinary Desmos.com. I accidentally looked at a matrix calculator. We're not going to do any of that in this. Well, actually, maybe in the last unit. Right. So Desmos.com. If you have an account, which I wouldn't expect to be the case at this point, but if you have an account, you can go ahead and log in. But otherwise, you could just go to Graphing Calculator. Right. And if you're doing it on a full screen, it's going to look a little different from this, but it's going to have the same ingredients. All right. Let me see if I can actually do that real quick. Yeah, so on a full screen, this is what it would look like. All right. And then you'd hit that little keyboard to bring up all the different mathematical operators. All right. But like I said, we're doing this with a split screen. And you can do it with a phone too. And it'll come up like this display if you do it on your phone. All right. There's an app, but honestly, I don't think you need the app. All right. So if I want to find the mean of these total of 7 values, I could add them all up and divide by the number of values in the set. All right. In Desmos, it's kind of strange. If I did, I'll just show you. It's kind of the wrong way to do it, but let me just show you real quick. So if I add all these values together, oops, plus 8 plus 0, and then go to divide it immediately by 7, you see that it only takes that last number and divides it by 7. All right. So there's 2 ways to handle this if you want to do it all in one shot. One way would be to use, there's a mean function. There's a function stored in the calculator that'll find the mean of a set of values. All right. The other way, or another way, would be to put parentheses around the values and then divide by 7 after the fact. All right. And that'll give you the mean. All right. So you can do it that way. Personally, whenever I do a complex division problem, as in, multiple operators in the numerator and then the division, what I do is I put the division in first. So I'll put it in divided by 7, and then right in the top. So to create a fraction in Desmos, you just use division and then tap into the top and type in the numbers that you want. right? And so that's a pretty a reasonably easy way of doing it. So what I'm going to do now that I know the mean, so I can just put off on the side here that the X bar value is equal to 4. I'm going to make a row here that contains only the number 4, repeated over and over again, corresponding to each X value. All right, because one element of this computation is X bar. So we just figured that out. You don't have to show the work for it. You just need to be able to find it. So then the next row would be X minus X bar. So I'm going to take each of these X values and subtract from it the corresponding X bar value. So it's going to look basically like this. I'm going to subtract these two, 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 with the X value coming first. So 2 minus 4, negative 2, 3 minus 4, negative 1, 6 minus 4, 2, 3 minus 4, negative 1, 6 minus 4 is 2, 8 minus 4 is 4, and 0 minus 4 is negative 4. All right. And if you want to make a nice looking table out of it, you know, you're more than welcome to. You just draw a couple lines here. Yeah. When it auto corrects, it kind of does whatever it wants. So sometimes I have to move it after the fact. But, you know, you can do something like this just to keep it organized. But if you're working with lined paper, you know, you're doing a problem for practice and you're working with lined paper, you already have lines there, so make use of that. Or if you have relatively decent penmanship, you could just organize it in the way that makes sense to you. All right. The next one, the next computation, if we're working inside out, this symbol here means sum. All right, so it's telling us to take the sum of all of the entries. So that's what this means. Taking the sum of all of the entries determined by this. In order to take the sum, because when you think of order of operations, multiplication comes before addition, and exponents are just another form of multiplication. And if you're going strictly by PEMDAS, then you would take care of any exponents first anyway. All right, so what I'm going to do is I'm going to take my row of X minus X bar values and raise it to the second power. All right, so I'm going to take each one of these entries, this one, this one, this one, this one, and so on, and raise them to the second power. All right, whenever you raise a number to the second power or any kind of even power, the result is always positive. So we're looking at 4, 1, 4, 1, 4, a couple of 16s. All right. You just got to be careful when you get technology involved, because I'll type in, for example, you know, I want -2 squared. It's going to tell me it's -4, right? But that's because it's interpreting this expression as -1 times 2 squared. All right, that's what it thinks we're doing, which is really not at all what we're doing. All right, what we want, in fact, instead is -2 in parentheses squared. That gives us the appropriate value. But I just think it's a little bit more convenient to think in terms of even powers giving you a positive result, odd powers giving you a negative result. Well, not necessarily negative, but odd powers will give you whatever the sign is that you started with. So if it was negative, it would remain negative. If it was positive, it would remain positive. Good news is we're not really going to work with odd powers. We're only going to work with the power of 2 for the most part. So drop the negative essentially. All right, but we do have to take care of that sum component, right? That capital sigma, the funky looking E, that's got to be part of the process, part of the conversation. So what I'm going to do is just simply add the values together. So I'm going to take each of these values and add them. And that's going to give me the sum of X minus X bar squared. So 4 plus 1 plus 4 plus 1, that's 10, plus another 4 is 14, plus 20, plus 16 is 30, plus 16 again is 46. That number right there is the sum of X minus X bar squared. All right. So that's what we're looking at. So basically we have the top of the fraction, right? This fraction here, I have the top now. So I'm going to get the sample variance. And that's going to be S squared is equal to this expression the 46 divided by n minus 1. N is the number of values in the set. Right, so just that n is the number of values. So in this case, n is equal to 7. Because I have 1, 2, 3, 4, 5, 6, 7 values. Even the 0 counts. All right, so I have 7 values. My denominator is going to be 7 minus 1. All right. Now the sample standard deviation is just going to be the square root of that number. So S would be equal to the square root of 46 over 7 minus 1. You could simplify if you want, but if we're going to use the calculator to figure out the result, and it's going to give us a decimal anyway, why not work with the least restrictive type answer? All right, so no simplifying, because what if I make a mistake? So now I could just type in a radical, pop in the division bar, which makes a fraction, 46 over 7 minus 1. So I'm looking at 2.769 approximately. We denote an approximate using a squiggly equal sign, and we round to 3 significant digits. So 2.769. All right. So 2.769 would be my sample standard deviation. Now, what that is it's a comparative measure. It's a number that tells us the on average what the spread of the data would be. But we don't really have an idea of what that 2.769 means until we have something to compare it to. A data set that's more spread out or less spread out. All right. So without that information, we just look at this and say, okay, well, there is some spread. Right? Any non-zero value, and they always have to be positive anyway, would have to indicate some sort of spread. If the sample standard deviation is equal to 0, that means that every value is identical, right? That there would be no spread whatsoever to the data, right? Now, if you look at the second example, just looking at just the X column, we have some frequencies here, but just the X column, we're looking at a data set that seems to be more spread out than the previous one. In number 1, the smallest value is 0, the biggest value is 8. In number 2, the smallest value is 10, the biggest value is 52. That's a more spread out data set. So I would expect the standard deviation for this to be bigger. How much bigger? Well, we'll see, right? But the good thing is, now that we've gone through an example where I showed you how to find the standard deviation, well, that's done. We go on to technology and let that do the job for us. All right. So we're going to check over number 1 using Desmos just to make sure that everything is the way it should be. So, you didn't make a mistake somewhere. And by you, I mean me. And then we're going to get into how to do it with a frequency table. All right. So first off, let me walk you through some of the functions that are stored in Desmos. All right, I might have given a little brief overview, but let me just do the statistics related stuff. All right, so if you go into functions and scroll down, you see a set of functions. All right, mean, median, min, max, a whole bunch of things. But you'll also see STDEV. All right. Oh, well, I didn't want to do it that way. So STDEV means standard deviation. It's going to give you the standard deviation of whatever numbers you type in the parentheses. So if I do 2, we'll separate with commas. So 2, 3. As I add more numbers, it modifies the standard deviation. That's how quick it does the computation. 8 and 0. And ultimately, I get the same decimal value that I had before, right? Which is great. I mean, on multiple levels. 1, I confirm the answer that I came up with, but 2, and I think more importantly, we didn't have to do any work, right? But sometimes you want more than just one thing. Maybe we don't want just a standard deviation. Maybe we want the mean. Maybe we have to do this whole table thing, but we want Desmos to kind of help us along the way, right? So 2 things you could do. One would be to just go backspace the stdev out and select the mean function, for example. It'll create another set of parentheses, but you could just delete that and it'll give you the mean. That's, I think, a little less user-friendly than I would like. Okay, so what I'll do is, let me just clear out all this stuff, is I'll show you how to do it using a table. All right, because we kind of did it with a table anyway, so why not investigate that a little further? You see the little plus sign there, right above the blue box. That allows you to input, or I would even say change the type of input. The default is f of x expression, which is really just an empty field. You could put a note in there, and that's basically any string of characters. Like if you want to put words in there, but you don't want it to do any actual computation, then you just make a little note. It's good for titling stuff. You know, like here, like input your data below and you'll find the mean, you know, that sort of thing. And you could create folders, but really not in a way that you might expect. But we're going to focus on table here. It defaults to an x1, y1. So still looking at example 1, all I would do here is type in 2, enter, 3, enter, and it assumes the next value. It thinks, oh, you're doing consecutive values. Maybe you want 4 to go in next. I don't. I want 6 to go in, so I can always overwrite it, and then it gives up. It doesn't see a pattern to what I'm trying to do, so I just type in everything else the rest of the way. So 3, 6, 8, and 0. All right. So I have all my data stored in X1. Very important to remember. Well, you don't really have to remember, you just scroll, but have an awareness of what list you're storing your information into. All right. Because when I do standard deviation now, I go to function, I grab standard deviation. I don't have to type the raw list in it again. It's already there, stored in X1. All right. So very important. You know, any piece of software has its own, you know, well, I'll say quirks, but also, you know, syntax, and just it's kind of a way of denoting expressions. Here, when you want to put a subscript, any letter followed by a number will make that number a subscript. All right. So if I want X with a subscript of 1, like it says in the table, I just type in an X, nothing special after that, X1, and it'll automatically make it a subscript. All right. But maybe I also, like I said, wanted to find the mean. I could do the same thing. Go to mean and then type in X1. So now I have the mean and the standard deviation. And, you know, if you tap on the gray box and drag, it'll allow you to change the order of things. All right. So maybe I wanted the mean first and then the standard deviation. All right. So there's a lot of useful features here, and you'll see really there's nothing on the graph, and the graph is irrelevant, but it's there in case we need it. All right. So that's pretty nice. All right. Also, let's say I can't find the command I'm looking for, but I know it's something that works in Desmos. Worst case scenario, just type in the command. Right. You could do that by, oh, I hit the back arrow accidentally. All right. Wait, did I hit the back arrow or the forward? We'll find out. Oh, it saved it. That's a miracle. All right. you hit ABC and it brings up a QWERTY pad, right? Just a regular keyboard pad. And I can type in mean, for example. Now you see it's in italics at first, but the minute it recognizes the command as something that's usable by Desmos, it changes italics to ordinary font. Right? At which point I can just go back, open parentheses myself, and type in X1. All right. So if you think that there's a command but that should work, but you can't find it, just type it in and see if it goes to ordinary font. All right. So if I think, for example, potato is a command, it's still italics. Once I put in the whole word, if it's still italics, it's not a command that Desmos recognizes. But you'll also see right below that, below italics, if I don't use quotes, it's going to ask me if I want to add sliders. And I'll get into what all that means later on. But basically what it's asking is, do I want to treat the P, O, T, and A as a set of variables that we can vary the value of? If that's the case, then you would select whichever one you want to create a slider for, maybe all of them. If I do that, if I hit all, it'll bring up a slider for each unique letter, and it's going to treat the word potato as the product of different values. Like in an algebra class, if you write X next to a Y, it's implied to be X times Y. This is being treated as P times O times T times A times T times O. All right. And then this allows us to determine what the product would be for certain values of P, O, T, and A. All right. So when that happens, don't be alarmed. It doesn't mean that you did anything necessarily wrong. What it usually means is that you either didn't use parentheses when you should have, or it's just not a recognizable command. All right. So, but I wanted to show you how you could do this sample variance and sample standard deviation with a frequency table, because it's a little bit trickier. But what I did was I created a calculator for you. So if you go into, I don't want to lose the screen share here because I'm just so thrilled that it actually worked today. If you go, I'm just going to talk you through it. Under course content or just content, if you go down to towards the bottom where you see technology assignments, above that you'll see calculators, unit 1 calculators, unit 2, and unit 3. All right, we're living in unit 1 right now. So you would click on unit 1 calculators, and the very first one that you see there says measures of center and spread. All right, so measures of center and spread, that's the one we're going to pull up now. I access it a different way on the iPad, but in Brightspace, if you go to unit 1 calculators, right, so under calculators, unit 1, you'll see measures of center and spread. That's the one you would want if you want to follow along. If you don't, and you could always try it later. I do have to log in though, and this is where I find out that I'm sharing personal. Oh, actually, no, it's a miracle. All right, so measures. Yeah, it's much more convenient for you. I actually have to type in the title in a search in order to find it, because Desmos doesn't really do such a great job of allowing you to organize your completed calculators in a way that you want. But the fact that it saves your calculators after you use them, after you create them, that's really, I don't want to say a game changer, but it's really a nice feature. So, I mean, I have all these calculators that I've created over the years, apparently 398 more. There's a lot, right? So
How is this a new product? Because when I tell you, when I took math last year, that intercept slope thing would have helped me tremendously.
oh yeah,
Yeah,
it would have helped. It's not new.
it's not new. We didn't use that. We were doing everything by hand. So I did a lot of crying, but I see all of these exponential. Wow. Okay.
Yeah, there is a school of thought, like for a remote class that like me personally, I think that everything should be contained within the system. So if you have if you're taking a class that's online or remote, I would think that you would have access to an online or remote calculator. But if it's an in-person thing, that's a different story. But also I have found out over the years that just plenty of people just, they know Desmos exists, they don't know how to use it, or they're not comfortable using it. So that could have been the case there also. So if you select the appropriate calculator, which is measures of center and spread, you'll see that you have a drop down for a single list of data. All right. So, and I'll show you both of them. You have an area where you type in your information. I'll get to that in a second, but for a single list of data, it'll give you the mean, standard deviation, and the median. All right. Desmos has a hard time with the mode, like computing the mode. It's doable, but you need to involve a graph in order to figure that out. It's not like a pre-programmed function. All right. But what we want for the second example is for a frequency distribution. So these would be the computations that you'd have to do in order to come up with the sample standard deviation, sample mean, sample standard deviation. All right. It's different notation than we would use in the class. So I'm not gonna make you learn a computer language in order to be able to answer a statistics problem. So this would be a calculator that you'd be able to use just by accessing it on Brightspace. Even more useful, I would say, is once you've accessed it, assuming you have a Desmos account, which is free, and you don't get any, they don't email you, like they don't try to sell you anything. It's completely free. Maybe 20 years from now, I don't know, it'll be like Wikipedia, where you get a little pop-up that says, we do all this stuff for you for free. How about throwing us a few bucks? If anything, maybe 20 years from now, they'll start doing that. But for now, it's completely free and no strings attached. You can save all of these calculators in your personal account. All right. So if you're logged in, you hit the little three line menu bar there, and then you just save it. And you see the blue save button there. It'll save it. You'll be able to retitle it if you want. Then you can also share your calculators, which is going to be really important for us, because this little share icon right next to my name allows you to come up with a share link. Now, it's not a real-time sync share link. All right. So if you create a share link and then, let's say, submit that link as a solution to a problem on a test, but then make a change later, it's not going to update it. You have to create a new share link every time you make a substantial edit, I would say. And that's kind of a drawback in terms of the desirability of the app. But from a teacher standpoint, it's great, because you submit something and then, the test ends, and a day later you're like, oh, he hasn't graded it yet. Oh, I realized I forgot to put something in my Desmos. It's not going to update it on my end. So it's a little less of a concern in the area of the dreaded C word, cheating. So yeah. Oh, no, I don't want to open that. I want to go back to, now I've messed myself up here. Done. The thing is, when you want to split screen, you got to have an app open. And I forgot that for some unholy reason. So anyway, you'll see that each of these solutions, sample mean, sample standard deviation, they say undefined. All right. Also, one thing I don't like about Desmos, hopefully they'll take care of this at some point. You see where it says X with a subscript of BAR? It says that because there is no symbol in Desmos of X with a bar over it. So we have to denote it some way. So that's the way we choose to do it. All right. But you get those undefined answers because we don't have any data plugged in yet. So in my X column, I'm going to type in my data points for X. So 10, 20. It's going to think I want 30, but guess what? I want 35. 41, 52. And then my frequency values, I use a capital F in the app, but on paper I use the lowercase f. You can go back and forth between those two. All right. There are certain circumstances where you'll need to keep track of what's capital and what's not, but this isn't one of them. So I'm just putting my F values in. It's going to compute X times F. That's information, that third column. You don't need to do anything with that unless you are computing the sample standard deviation and sample variance and sample deviation. Try it again. Slow down, dude. Sample variance and sample standard deviation. If you're computing either of those two things by hand, that third column might be useful for you, but I'm not going to make you do it by hand. All right. So once I have my information in and I'm confident that it's typed in correctly, I didn't make a typo, hit the little drop down, and now I have some fresh new values for my X bar and my sample standard deviation. So my sample mean, they didn't ask for that, but I'm going to put it anyway. X bar is equal to, if we go 3 significant digits here, it would be 26.0541. Then the notation here, I guess I got a tap of my finger. The notation here says S sub F, but I titled it. I used a note right above it, sample standard deviation. So regardless of the notation that I'm using, this computation is a sample standard deviation. On paper, we denote that with an S, all right? Just like we did here. So 4.559. All right, that's the sample standard deviation. I also need the sample variance, right? Sample variance is S squared. So I need that one. And I only need it because that's what the question's asking for, right? If it doesn't ask for it, then you don't need it. So sample variance. It's not listed in my computations. I don't have a field that says, oh, by the way, here's your sample variance, but we could figure it out. So what I would do is I would type in SF, all right? So S, now I want a subscript of F. If it were a number that was a subscript, I would just type it right in straight away. I would just do like S1 and it would make it a subscript. But if I type in an F here, it's not making it a subscript, all right? What I'd have to do, right next to the 1, 2, 3 on the bottom, you see A with a little subscript of B. That's how you make a subscript containing 2 characters, right? So an S and an F. So hit this little button here and it'll bring up S sub F, right? And you can see it's the same number that we have in the previous field. So I know that I typed in something that's correct. I want to square this, so I'm going to raise it to the 2nd power. And that'll give me my sample variance. So 20.782. All right. So 20.782 would be my sample variance. Right. So you could go either way. You know, if you already know the sample variance, you take the square root of it to find the standard deviation. But if you know the standard deviation, raise it to the 2nd power, and that'll give you your sample variance. All right. So computationally, finding a standard deviation is not going to be too bad because we're just going to use really the same calculator, same Desmos calculator over and over again. So all of this work, I know it's kind of annoying. I hated it when teachers would do it when I was going through the process. This set of computations, I'm not going to ask you to do that. But I am going to refer back to it when we talk about other concepts like z-score, standard positioning, and things like that, right? So having gone through it the one time is really important because it gives us a sense of the underlying structure, but I'm not going to make you do it. So I have to imagine there's at least a couple of students that are like, why do we have to write all that stuff down if we're not going to do anything with it? I'm not going to make you do it, but we are going to refer to it, all right? Early in my career, it's a little bit more of a, let's do it by hand. Why? Because that's how I learned it. Now it's more like, let's do it by hand, but only if it serves a purpose. I just realized I got to change the date and time on my iPad. Anyway, measures of position. This refers to standard deviation, right? So measures of position we make those determinations based off of our knowledge of standard deviations, right? So every score can be represented in terms of standard deviations away from the mean, right? So what we think of when we're talking about relative positioning or the position of an entry within a data set is how many standard deviations that value is away from the mean, right? So if I tell you that, for example, just a quick one, if I tell you that the mean is 0 and the standard deviation is 1, what I'm saying is that this ruler would be measured in terms of those standard deviations. And so we would establish like which tick marks mean what. But I would say, for example, if I wanted it to be centered around 0, that each little tick mark, regardless of size, would be measured in 1 unit increments. I could do that way. But if you're really kind of treating it like a ruler, then you would say something more like, I'll write this back in a second, but I'll just show you real quick. Like if I wanted to call this 1 unit, then this would be 1/8 of a unit and so on. That's more of a traditional ruler representation. But I'm saying that each little space here, so this little guy would be measured in 1 unit increments, right? But just like in a function related math class, whether it's college algebra or pre-calc or whatever, anything basically not statistics that we offer, you could also have negative numbers, right? So this is in the positive direction. We think in terms of steps. So I'm taking 1, 2, 3, 4, 5, all the way up to 8 steps in the positive direction, but I could also go in the negative direction. So 1, 2, 3, 4, 5, 6, 7, 8 steps. So I label that -1, -2, -3, -4, -5, -6, -7, -8. All right. So if I were to compute a standard deviation for a simple data set and determine that that value is equal to 2.769, and then find the standard deviation of a completely different sample of data and determine that that sample standard deviation is 4.559, I have now a basis by which I can measure the two against each other. All right. So what this is saying is, instead of having, I'll just look at example 1 again. Instead of having each increment be 1 unit, I have a mean of 4 here with a standard deviation of 2.769. So again, going back to example 1, instead of being centered around 0, I'm now centered around 4. And each one of these little tick marks here would be, instead of 1 unit to the right, this one would be, it's going to be tough to write it in here, but I'll use a little arrow. This one here is going to be 4 plus 2.769. All right, because I'm starting off with the mean and adding to it 1 standard deviation. All right, so that's what this represents. Previously, over here, the mean was 0 and the standard deviation was 1. So that 1 that I first labeled here, that was 0 plus 1. The mean plus 1 standard deviation. It's the same action, it's just using 2 different values. Instead of 0 and 1, it's 4 and 2.769, right? So you can see how this will get pretty out of hand pretty quickly, because the next one would be 4 plus 2 of those 2.769s. That's the same as saying X bar plus 2 times whatever the standard deviation is. All right, so it gets a little messy, or very messy, very quickly. But the same concept is at work. All right, we could also go the other way. So for example, if I wanted to go to this location here, that's 3 steps to the left. So 1, 2, 3 steps. This one would be the same as saying 4 minus 3 of those standard deviations of 2.769. That's the same as saying X bar minus 3S. All right, very strange, but very useful, because the scale makes or allows you to make a determination of spacing. All right, so if I tell you in this data set, I have a number like 10, how far is that away from the mean? You can count in increments of 2.769 away from 4 and come up with that value. All right. You can also, I mean, you could do it using technology also, you know, just to get an idea, and then you'd figure out what the placement is. So if I did it using technology, I would just keep it simple. I would have 4 plus 1 times 2.769. It helps if I hit the right button. 769, right? So 1 unit away would be 6.769. And then I would just do that again, replacing the one with a 2, replacing the one with a 3, and so on. And that would give me all the individual measures that are associated with the ruler, right? It can be a little much. We don't want to have to label out an entire ruler with new metrics. So we just think of it in terms of standard deviations, because the underlying principle would be the same. You would just be changing the values along the way. There's other little shortcuts in Desmos that'll get us there, but that's the gist of this idea of measure of position. What we would do is establish the location of a number within our ruler and then use that to compare to another ruler, right? And we'll see more of that. There's shortcuts. There's plenty of easy ways of doing it. It's just not always the most user-friendly thing in the early goings. All right. So that brings us to something called the empirical rule. The empirical rule is really important because we can use that to make a determination of whether a distribution is considered to be normal. Right. So a normal distribution is a symmetric curve, bell-shaped. I mean, that's the best I can draw it. So pretend that's symmetrical. I'll try it again. I always like to give it a couple of shots before I give up completely. All right, that really is the best I can draw it. I know it doesn't look perfectly symmetrical, even slightly symmetrical, but that's what a normal distribution looks like. And so if about 68% of the data lies within 1 standard deviation and about 95% lie within 2 standard deviations of the mean, and about 99.7% of the data lies within 3 standard deviations of the mean, then we would say the distribution is considered to be normal. All right. So what that means is that we have to establish our ruler based off of this idea. but the ruler is just going to be along the x-axis. All right, so the way we label up a normal graph, normal distribution graph, is by placing x bar right in the middle and then counting out 3 steps in each direction. All right, that first part of the ruler would be x bar plus 1s. The second tick would be x bar plus 2s, and then x bar plus 3s. X bar being the sample mean, and S being the sample standard deviation. I try to make my my S's look really S-y rather than really 5E. Yeah, it's very easy to mess up your understanding of a concept based off of the way you write something. Because I've had plenty of instances where people would ask, right, I understand everything else, but where did the 15 come from? Where did the 25 and 35 come from? So, just little things like that, based off of just something as simple as penmanship could be an issue. So just take care of that. So X bar minus 1S, poor quality S, right on cue. X bar minus 2S, and X bar minus 3S. That one really looks like a 5. All right. So what this rule, this empirical rule, is saying is if in this region of the graph, you have about 68% of the data. This is how I know it's not really symmetrical. This other part of it should have been like over here. Again, it's not an art class, so not overly concerned, but it'd be nice, a little bit better. So about 68% of the data should be in this region. All right. Then the second region should contain about 95%. And then the last range, the last interval, should contain about 99.7, which is oddly specific. Because like about 99.7 isn't 99.7 pretty exact to begin with, but that's the rule. So about 99.7% would be in this interval. And you don't have to tolerate my crappy drawings. This is something you very easily find with a quick Google search. So normal distribution or normal curve, and a lot more creative people out there than me, and they come up with nice ways of visualizing it. All right, but yeah, these percentages, this is what we're looking at. If we can establish these percentages to be true based off of this graph and the data that corresponds to it, then we would be looking at something that's considered to be normal, or a normal distribution.